Hello, everyone. We are now in week 10 office hours. Let me see whether everything's working okay, unlike last time. Okay, I cannot do that because if uh, let me see, actually, I think I'm trying to, yes, good, okay. We have video and we have audio. I was trying to join the same, to start the same office hour session again, so that was the problem. Okay, so a week 10 of office hours. Last time Tony had held office hours. I understand he too ran into some issues with our usual setup, but hopefully we're not going to have any additional problems. We'll see what will happen following office hours. So next week we have spring break. There will be no office hours, and then the following week, both Tony and I are at a conference in Europe. So we'll do this together from there. We'll have to figure out a time zone and a place where we can do it from, but we'll sort that out and we'll let you know. So where are we right now? You have received the grades for Project 1. Those were distributed. By now, I think that you know that if there are some questions regarding the grade, you can always put a private post regarding the project grade and just put it visible to all instructors. Whoever of the TAs graded your submission, they'll be able to explain to you if it's unclear to you exactly where the problem with your grade was coming from. So you have the Project 1 grade. I will officially unmute the grades for the midterm immediately following office hours. To give you some context, I finished the grading this weekend. Well, last night, really. This was the first time that we hosted the exam in Canvas, and it turned out that it's not necessarily the most that it's not necessarily the friendliest platform. Before we hosted the exam in T-Square, and I also had it hosted in ProctorTrack itself, at least once, I think. And Canvas threw another set of curveballs at us. I guess the two most fun were, one, when it generates the spreadsheet it generates basically in the spreadsheet a column per question, and then all the answers are in that column. And it turns out that it delimits the different options, like in the multiple choice, multiple selection, or in the multiple fill in the blanks, with a comma. And of course, if your answers itself use comma, then it's kind of impossible to spread that, to parse that list and separate the individual answers in a separate column. So that and the problem was that there were some of the students that chose to use a comma for some of the decimal numbers in the answers and in one of the questions. And that made that grading a little bit more challenging. And the other one, the much more bizarre, which I really don't understand the rationale for it, is that sometimes the way it would generate a set of answers in a column. And so sometimes it would be, the answers would be in order. So if you had like A, B, C, and D in the question, it would generate the answer for A, comma, the answer for B, comma, the answer for C, comma, and D. And sometimes it would just reorder these. So the first element would correspond to, the fourth or the fifth or the seventh answer, the seventh fill in the blank, for instance, and then the others would follow. And of course, I didn't detect this immediately, so I was a little bit panicked by kind of when looking at the scores of the exam, that they were just really much lower scores. But that's because it took me a while, and even on like simpler questions, it took me a while to realize that that there was a reordering, and there is a one secret place in Canvas where you can go and find out exactly what was the order that it chose to use when it was generating the spreadsheet, and then things became easier. So I finished grading. I will release the grades. I'm not really sure once I release the grades and of what are the options of, I think that you will be able to see your responses, and then and the kind of the appropriate correct responses, but that are configured in Canvas. But if that's not the case, we'll sort of worry about that afterwards, how to make sure that both you can see your responses and that you can see what are the correct responses for the questions on the exam. So I think that all of that will be visible, but as I said, we have not used Canvas before, so I'm just going to wait to be surprised potentially. One of the things that fortunately we had a student who took the exam early, and the student who took the exam early, turned out that by default Canvas actually produces a grade for once you take the exam, and by default it just that grade is visible. Unfortunately, it does not, as a system, it does not allow me to explain how I assign partial credit. So it was just using these kind of all or nothing, and so the student observed a much lower grade than what it would have earned. In fact, Canvas kind of auto-graded all the submissions, and then once I eventually finished grading the submissions correctly, I could see that with the way that we distribute points and provide partial credit, etc., for all of the questions, every one of the students ended up scoring much higher grade than whatever Canvas was going to assign to you automatically. So I will also share with you the distribution of the grades in terms of how the scores are distributed. Just as a summary now, let me scroll down the 400 something submissions. So the mean is 79, the median is 80, the maximum is 99, and the mean is 35. Actually rounded up every one of the points to a full integer. But even before rounding them up, pretty much it's 78.8, maximum 98.75, and minimum 34.5. And the overall distribution looks kind of similar to what we've seen in the past. So we'll share that with you after the exam. So at this point, you will have the grade for Project 1 and the grade for the midterm exam. And we talked a little bit about grades and curving and how great the final grades are assigned in this semester. I still see that there are questions on this topic that pop up on Piazza, so I'll try and go back and if I see those questions, to reference them to office hours, and in case they've missed some of the earlier discussions. But let me repeat one more time here. What we do in this class is in general, in at least most of the graduate level classes at Georgia Tech, the ranges for the letter grades are a little bit broader than what typically is the case with undergraduate level classes. So whereas at undergraduate level classes, it's very common that an A would be only from basically from 90 to 100. We broaden that range. It has to do also with what constitutes passing versus failing in general in graduate level classes. It's not just that in this program with some of the entry level courses, you kind of need to have an average of a B in order to fully matriculate in the program, but you also need certain distribution of grades in order to be able to complete your course requirements and specialization requirements. And I think that's what really drives how some of the grade ranges are determined. I don't want to commit to anything at this point because we kind of take overall the grade distribution of the whole class at the end of the semester into account when we determine what are the actual grade ranges, letter grade ranges. In the past, the cutoff for A has been somewhere between 80 and 84. I understand that that's not a small range. It's still quite a number of points, but it has varied somewhere in that range. And then the cutoff between B and C has been somewhere in the low 60s, around 60 even. So what that tells you is that at this point, you have completed the midterm exam, you have completed project 1. Combined, the two are worth less than 40 points, 40% of the grade, right? Because the projects are 3 projects total worth 40 points, and then the midterm's 25. The final is 30 points, and then the exam, and then you get 5 points for participation. So what that means is, let's say you've scored, let's say you kind of didn't do as well as you had hoped, and your average is around 60 points between the midterm and the final and project 1. What that means is that, basically from the overall grade of the semester, you've really lost like 15, 16 points, right? And this is kind of me doing math quickly. I should have picked just an easier number, like your 50% average. There are plenty of points that are remaining that you can earn in the remaining assignments. That you can, as long as you make sure that you're doing that you're kind of doing well in the remaining assignments, that you do well in the final exam. There's basically, even if you haven't done too well in these 2 components of the class, you still have a chance of even earning an A, right? Provided that you obviously get as close to the maximum number of points of anything that's remaining. Students, we often see students express concerns because maybe their midterm is around 70 and their project's around 70. And I would advise you not to be too concerned about that. It doesn't mean that 70 is a C, like what you would maybe you were used to in your undergraduate level classes. So in addition to the actual sort of the regular part of the points in projects 3, 4, and in the final exam, there are some extra credit opportunities within these assignments. First of all, if you kind of do extra well with some of the components of the assignments, the TAs can assign extra credit, and then there'll be some explicit opportunities for extra credit. And in addition to that, there is for all the cases when a student is kind of in between grades, we are going to, in those cases, really look at your submission to Project 2. So there are plenty of outstanding points. Once we release the grades for the exam, you can kind of think about where you are. And then one of the things that I did say before is just really try to think, if you have not done that well or as well as you'd wanted to in the Project 1 and the midterm, Obviously, there is a lot of room for you to do well, but provided that something changes in how you're operating in this class. And so ask yourself whether kind of the main reasons why maybe your performance was lagging in the first part of the semester, whether those reasons have sort of been have disappeared. If it was because you had some situation at work or personally that was not letting you put the time in, has that changed in the second part of the semester? If it was basically simply because kind of really you really didn't have the right background coming into this class, then ask yourself, are you really managing the material better? Looking at project 3, we said the first part of project 3 is really not fundamentally new material. I mean, yes, you learn some of the new things about curl APIs, etc., but essentially it's still C programming, dealing with threads, right? The kinds of things that you were supposed to get some exposure to and also learn in project 1. And so if you're at least doing, you can tell that you're doing better with that part. That means that kind of some of your programming, some of those deficiencies have been overcome, and so there is reason to expect that you will be able to do better in the second part of the semester. So that's the advice that we typically provide, and kind of in principle, we see that students overall, that the class as a whole tends to do better in the second part of the semester. So we expect that will be the case again. Of course, that doesn't mean that that's the case for every single student. And again, the key reason is, especially if you're really underperforming in this part of the semester, then the key reason is when you're thinking about what to do and what to decide in terms of the drop date, is to think about, are those reasons still there, or has there been a significant improvement in kind of you being able to overcome those gaps that maybe slowed you down and affected your performance. When we release the midterm, similarly with the project 1, you can put a private, in case you have some issues or some questions about your grade, you can put a private post and tag, make it visible to all instructors, just so that in case I miss some of these, the other TAs can alert me. But I'll try to get to your questions and provide some additional explanation. I will probably the results will kind of the information about the grades will come into 2 parts. One, just the generic about the grades are released and here's the distribution. And then I'll verify exactly what is and what isn't visible from a student perspective. And we'll let you know how you can find out specifically what are the questions where you did wrong. I think you will be able to see both your answers and the answers that are marked as correct in Canvas, but I'm not 100% sure exactly kind of what Canvas will decide to show you. Okay, so I think that's all I'm planning to say at this point about the grades. So let me just put a note. In case somebody wants to listen to this part alone, so they can find this part. Okay, so let's see. So in terms of the material, we are so project 3 is released, the expectation is that we release the project 3 immediately after the midterm, but we're sort of expecting that you spend a little bit of time first just catching up maybe on the lectures from part 3. And so the first part of the project was really more of the generic part, general C and multi-threaded programming. And then in the second part of project 3 is where you really get into some of the new material. And in this particular project, the new material is related to interprocess communication, and that's captured in lesson 3 of part 3. I know Tony talked about project 3 last week during office hours. And the lesson very much gives you some illustrations on how you can use the different APIs for interprocess communication. Some of the things that where we suggest that you guys end up next week in particular is spring break. So this will at least in terms of maybe new suggested material that's not going to introduce anything, so you have maybe some extra time, and there's going to be no tests, etc. So that gives you some extra time to maybe both catch up on the lectures and to also find the time to make progress with project 3. My expectation, recommendation, whichever way you want to say it, or interpret it rather, is that by now you are done with reviewing the material that's needed for project 3 and that are already working on the second part. A simple suggestion would be to maybe try out some TOE examples, a little bit maybe like what's illustrated in the lecture, to get an understanding of exactly how these different mechanisms for interprocess communication, how they work. Maybe decide what are more useful APIs for you, and then to actually move on and start implementing the IPC-based communication between the proxy and the shared cache in project, in the simple cache in project 3. One of the things that we typically advise students is to sort of really spend a good amount of time designing, maybe pencil and paper, whichever way works for you, designing exactly how is both the control information between the proxy and the cache, as well as the actual data, the actual responses, how are all of those interactions going to happen? And there are a number of decisions that you have the flexibility to decide on, but that also you also have responsibility to make those decisions. And so it's important to make sure that you kind of give yourself some time to come up with a sound design. It may be based on the suggestions that are given in the lectures. You may come up with a design of your own. The number one requirement that's kind of really important for the project is that you have to make sure that the actual transfer of files between the cache and the proxy happens via shared memory, right? And then you have to make sure that you're not limiting the system in some way where you end up with an assumption that you will be able to create a shared memory segment that's sufficiently big to hold an arbitrary file, or that you're able to create as many shared memory segments as you wish, etc. So instead, you have to make sure that your design works for the case where the size and the number of the shared memory segments is specified externally, and so a single file transfer, so single request that's coming from a client, and then is serviced by a proxy, a thread in the proxy and a thread in the cache, that request, the file transfer that's needed for that request uses only a single shared memory segment. So that's kind of very important. So there are many different ways how you can end up with that design, but that feature has to be there. In terms of other features, you have more flexibility. So things that you need to decide on is basically how are the thread in the proxy and the thread in the cache going to agree upon what is the shared memory segment that they need to that they're both going to use, right? So they both have to identify and then use the exact same shared memory segment. So the actual information regarding this the segment ID somehow needs to be passed, communicated between them. That you have flexibility. How are you going to pass that information? You have flexibility to decide who is going to make that decision in the first place. Is it a thread in the proxy that's going to decide on what's the shared memory segment that will be used and pass that information somehow to the cache, or the other way around? You have so that's basically, so you have some flexibility there. You have some flexibility in deciding kind of exactly how these two threads are going to communicate. Are they going to communicate via some designated shared memory segment that's going to be just used just for control information? Are they going to communicate via some other IPC mechanisms, via message queues? So that's another thing that you should decide on. One of the things that we said very early on in the beginning of the semester, in the introductory lecture, we said that when processes communicate, they have the ability to rely basically on the kernel for all of these operations, like when you're using some sends and receives, and all of the synchronization, the blocking, etc., is handled in the kernel. Or you have the ability to just request, give me a shared memory segment, but then in that case, you, the user, has to implement everything, not just in terms of the actual transfer of the data, but in terms of also the synchronization of the two threads. A thread now, in this case, two threads from two different processes, a thread from the proxy and a thread from the simple cache. How do they make sure that they don't end up with some race condition when they're trying to read partial results or overwrite the results before they're read or something like that, right? So you're going to have to implement the synchronization, implement the blocking that maybe needs to be there in case there's no one has written data, or that the buffer is full and one of the threads needs to wait for the other thread to finish reading it. So you have the flexibility, and so how you end up implementing this, you can use, there are a couple of options, both in terms of using mutexes and condition variables, using semaphores, and etc. I've seen multiple times comments from students. I remember that there was a student that said that the students spent basically quite an amount of time just with pencil and paper and absolutely nothing else, until they kind of really felt comfortable that they've worked through all aspects of the design. And then once they did that, the actual coding of the project ended up being something that they were able to kind of completely finish within a matter of just a few hours. The kind of debugging that basically would need to go through, and that doesn't matter whether you're doing pencil and paper or not, is kind of really think through what happens when you just have a single request, single thread in each proxy and cache. And so you just need to go through the set of steps of passing the request, all the control information, and getting the response. So basically, first, just enabling the communication synchronization via these IPC mechanisms. Second, making sure that now these, this multi-threaded, these two threads from the two different contexts, that you've resolved all of the concurrency related issues that can happen across processes while a single request is being serviced. Have you taken care of the case where the request is an error message? Have you taken care of the case when the request is smaller than the size of the shared memory segment? What about when it's really just the request completes the full size of the shared memory segment, like these corner cases? What about when the request is larger than or basically when the file the response is larger than a shared memory segment, or it requires a full integer number of shared memory segments? Make sure that the response that's being returned from the simple cache, it's not just the file. There's some metadata that's part of the response, some metadata that may be used for synchronization, that's maybe used to provide some information that's really part of the header, or some additional information about the size, the end of the file, etc. So you have to make sure that there is room for all of that. And so that's basically, once you work through all of the issues with just using shared memory and using these IPC mechanisms in the first place, then work through all the issues related to some of the concurrency problems that may come up in this case that you have to solve, right? If you were just using kind of a socket-based API, a lot of these things would be hidden from you because somehow the kernel deals with allocating buffers, making sure that there is enough room, making sure that kind of it keeps track of kind of coupling the send with the receive and not just returning some junk. So all of these issues you have to resolve yourself, and then you have to make sure that this all works when multiple requests are being handled at the same time. And so kind of how do you recycle these shared memory segments? Once you're done using it, you return it to a pool, you pick up from a pool, do not allocate them dynamically. How do you worry about the fact that now you have multiple requests, information about multiple requests that needs to be passed from one process to another, right? So this is going to be basically the control mechanisms that you chose to implement. This needs to, and if you need to solve all of the concurrency issues there that may arise, not just because of the threads from two different processes, but also because of the threads within the same process. Then there's a question that came up a couple of weeks ago during office hours. If you're not using some thread-safe APIs, you may run into problems there. So what happens, for instance, when all of your requests are requesting the same file? So some of these things potentially you ran into in Project One and have worked through Project One. In Project One, potentially you could have implemented some things in maybe some naive ways and kind of work around some of these issues, but they may come up now. So that's the advice for Project 3, and so compounded in that is the fact that kind of take this time these next 2 weeks, because we're not going to have office hours next week. So take this time this next 2 weeks to make sure you've caught up on everything that you need to do in order to be working on the second part of Project 3. 2, you have enough of advice on getting started with this part of the assignment, on some typical problems that come up with it, and so hopefully this will give you enough information to get going. And again, we're not going to have office hours, but in terms of Piazza, we will be around. The other thing that you need to be working on, so the official lesson for this week is the official recommended lesson for this week is lesson P3L4. This is a lecture on synchronization. And it goes along with a Superfund paper that's looking at the performance of several spin-lock implementations. So just super quickly, one of the things that came up on multiple occasions was, we told you that basically, without really knowing exactly what's happening underneath, you cannot assume that you can kind of simply have a statement where you're maybe just checking the value of an integer that's shared among multiple processes. You cannot assume that you can just check the value, read or write that value without actually using proper locks, unless you know exactly what the hardware behaves like, how that that integer is implemented in memory, etc. And so the reason for that is we have parallel hardware, we have multi-threaded, multi-core hardware, also hardware multi-threading is what came up in P3L1 also. We have multiple caches. And so we really, when we are reading result, when we're writing or writing to a variable, we really, without knowing exactly how the hardware behaves, we cannot make any guarantees that that particular operation is actually going to be atomic and not somehow be basically end up taking multiple cycles and because of that end up getting overlapped and interleaved with some other operations. If you want to have some operation that happens atomically, you have to rely on hardware-supported atomic instructions. And depending on the kind of system that you have, there'll be different atomic instructions. And depending on the kind of system you have and the kind of atomics that you have, how you end up implementing some higher level synchronization constructs like mutexes, like condition variables will differ. And so what this paper is about, it looks at a very simple synchronization construct, spin lock. It's very basic. It's pretty much kind of a basic construct that's used as a building block in more sophisticated synchronization primitives. And what this paper does, it looks at several different ways how you would implement something as simple as spin lock on top of the hardware, on top of the atomic operations that are supported by the hardware, and then what are the different trade-offs that are associated with these different implementations in terms of several different metrics. We already talked about how when you're making when you're designing something, you need to know what are the objectives of that design. And that kind of ends up getting defined by basically that ends up influencing the metrics that are important. So maybe the metrics are, and if you want to, your system's mostly going to be underloaded. So then what you really want to make sure happens is that in the common case, when there really isn't contention, you want things to be as fast as possible. Or maybe your system is going to typically run with many threads, and so contention is going to be the common case. And so then what you really want to make sure is that in the case of contention, your system performs well. So these would be, for instance, some metrics that are important. So look at the lesson, read the paper, and then I'm sure there'll be other questions. There'll be many questions about that, and we'll talk about that in office hours in a couple of weeks about that and the remaining topics. And so now let me go back and find, there was this one question with today's office hours, and this question was about the O of 1 scheduler in Linux and its kind of mysterious use of this active and expired list and what was happening with priorities there. So it's a little bit, so first of all, and if you look at the lesson P3L1, when we talk about scheduling, we first give you this example of this multi-level queue structure that that kind of makes sense to use for. Well, first of all, we tell you that if you just have compute-bound tasks that just really they just use CPU, not interactive, that you're better off of just letting them run without interruptions, kind of giving them the longest time slice possible, right? Not introducing the overheads of the scheduler, of making a decision which thread to pick, and then dispatching that thread, running the context switching, etc. That these scheduling overheads are important, however, when you're dealing with tasks that are interactive, because they'll just do something for a little bit and then they'll wait on I/O or generate I/O, etc. So then kind of it's a given that you will be paying for these scheduling tasks. So we give you this intuition that it makes sense that if when you have interactive tasks, the norm is that there'll be short time slices and the scheduling overheads will basically be common, right? Whereas when you have compute-bound tasks, that you're just better off with long time slices. And so then the next question is, well, how do you know what kind of task you have? So then we give you the multi-level queue structure, and we say, well, here is a way how you can kind of easily guess. So you start off with giving your assuming that your tasks are I/O intensive, and so assigning them some small time quantum, right? And so if the task indeed completes within or yields blocks, right, generates an I/O or blocks because it's waiting on I/O in less amount than that time quantum, then good guess, right? It was probably a I/O intensive task. And then if it took longer, if you had to preempt it, well, maybe it's not as I/O intensive as you thought it was, and so you're gonna push it to a lower level where you're giving the tasks longer time quantums, and then kind of the most compute-intensive task, you're giving them largest time quantums. And then there is a mechanism how your tasks are going to basically move up and down that queue. And so then once we tell you that, then we show you what was done in the Linux of one scheduler, where there are kind of couple of differences. The first difference is that we say, well, the I/O intensive tasks are the ones that have obviously higher priority, and there is this bigger amount of time that's associated with them compared to the compute-intensive tasks, the low priority tasks, right? And so that kind of is opposite of what we talked about, but it's opposite than what we talked about just because of how this active and expired arrays work. So the way that this time is used, an I/O-intensive task will keep using whatever, like a tiny little bit of time that really needs to run before it generates I/O, and then it continues associated with the active list until it ends up consuming all of that big chunk of time that was initially allocated to it. So if it had a time slice of 200 milliseconds and it's just running a millisecond at a time before an I/O event, so for 200 times it will basically run, compute, and then go back in the active array at its priority level. And only once it consumes the entire amount of time, only then will it actually get moved to the expired list. So, and the same thing will happen with all the tasks in the system. So regardless of the priority of the task, a task will remain associated with the active array until it has run enough times to consume the total amount of time that was associated for it, given its priority level. And then it gets shifted to the expired list. Now, the problem with the scheduler was that what would likely happen, so you have high priority tasks and low priority tasks. And so if you have both of these types of tasks at the same time, the high priority task end up kind of, running there a millisecond at a time, wait for an I/O event for 200 times. And then ultimately they all get shifted on the expired list. And so technically in the system, now you have high priority tasks that are runnable. It's just that they can't be scheduled because they're on the expired list. And they have to stay on that list as long as every single task that originally existed on the active list doesn't run enough to complete the full extent of its time slice and end up going on the expired list. So let's say, I don't know, hypothetically, let's say, you had, a couple of high priority tasks that were kind of executing like this, run for a millisecond and wait for a millisecond. So basically, you were constantly running these tasks, these two high priority tasks. And they pretty much, whenever they needed to run, in this kind of hypothetical scenario, two high priority tasks, they each need to run for a millisecond, wait for a millisecond. So basically, whenever they needed to run, they would get scheduled. And that would go on for essentially 400 milliseconds, right? Until each of them consumes its 200 millisecond in an interleaved way time slice. And let's say at the same time, there were also two low priority tasks that were just waiting in the active array. So the problem is now these two high priority tasks, they consume their 200 milliseconds each. They get moved to the expired array. And now all of a sudden they have to wait for the low priority tasks, each of them to consume their 10 milliseconds, right? So they were running in this kind of constantly, right? And then they're moving in the expired list and they have to wait for the two low priority tasks to run for 10 milliseconds each for the 20 milliseconds. So the behavior of the scheduler, that once a task moves to the expired list, it cannot run until every single task from the active list from the active list does not execute the full amount of time that's allocated at that priority level and moves to the expired list. That behavior, that's true for any task, no matter at which level. It's not a big deal if the low priority task now needs to remain in the expired queue for a longer time because they're in the system overall. There are still high priority tasks on the active list. Like if I'm thinking about the system, I have high priority tasks and low priority tasks. Okay, the low priority tasks are non-running, but the high priority tasks are, right? The problem is the other situation where my high priority tasks consumed all the time that was originally allocated to them on the active array and are now waiting on the expired array for all of the lower level tasks from the active array to finish their execution. So I think that your question. So basically, the question is, it's the behavior. So to answer the question is that this behavior is true regardless of the priority level. You're right about that. It's just that it's really a problem when you have a situation of high priority tasks that are runnable and are waiting on the expired list because low priority tasks are still consuming their time quantum. So if it's still not clear, then you can put a follow-up question and we'll try to further resolve it either via further answer this question either via Piazza or to further add to the explanation during next office hours. So, okay, so that's it from me. I think I want to make sure that we reiterate some of the advice for what to do with Project 3, and then we give you a little bit of a heads up on what to expect from the grades. And then we will see you in a couple of weeks at this point, not 100% sure what time or time zone we're going to schedule the call, but at some point Monday, Tuesday after the spring break, and we'll check on any open questions from before, give you some last bits of advice for project 3, and then maybe we'll talk about some of these lecture topics that include several papers in this group of lessons from the second half of part 3 from the lectures. Okay, so see you in a couple of weeks, and thanks for watching. Bye.